Okay, welcome everybody to our 51st episode of SBCL Cast, and we are very happy that we could convince Nicholas Fraser from AMD to tell us about deep neural networks and the optimization of these deep neural networks specifically. So now I'll give it to Martin to introduce Nicholas.
Thank you, Torsten. Nicholas received his PhD at the University of Sydney and is currently a research scientist at AMD Research and Advanced Development. His main research interests include training of reduced precision neural networks, software-hardware co-design of neural network topologies, and audio signal processing. Thank you for joining us today, and without further ado, the stage is all yours.
Thank you. Okay. All right. Can you see the slides okay?
Yes.
Perfect. Okay, so thanks so much for having me. So I'm Nicholas Fraser. I'm from AMD Research and Advanced Development, or RAD. I'm gonna start with a quick apology. My mind maybe wasn't working so well when this talk was when I was scheduling the date for this talk. So it turns out that it is Halloween night in Ireland, and Halloween is very popular here. So I've unplugged my doorbell, but people also like to set off fireworks in Ireland. So I've kind of shut myself in, and I'm hoping to have no distractions. But if you hear loud noises or door knocking or things like that, you know what that is. So I'm here talking about neural network quantization, and in particular with this open source tool, PyTorch-based tool that we've made at AMD called Brevitas. I wanted to start with a quick sort of summary of what we're going to talk about today. So quantization, if you don't know, is one of the key techniques in enabling deployment of large-scale machine learning models, and that's why we're interested in it, right? So Brevitas is our PyTorch-based tool. It's a research tool, a library that we use to try to do quantization experiments and try to meet certain accuracy targets or inform new hardware that we're going to design. And our main focus is achieving high accuracy. So given a particular quantization format, how can we maximize the accuracy of that model? It's pretty flexible. It has support for all your favorite data types, integers, mini floats, and even these new group-wise data types. And as I said, because we sort of use this to inform potentially new hardware, it's also easy to define your own data types. Finally, it's open source, modular, extensible. We built it to enable our own quantization research. And I would say part of my ulterior motive for this talk is to maybe convince some of you that it could be a useful tool for enabling your own quantization research. And this would be something that I'd love to hear from some of you about. Maybe after the talk, please reach out if you're interested in learning more and trying to leverage Brevitas maybe for your own research. So quantization. So what are we talking about here? Why is this important? Okay, I'm sure many of you have seen a chart like this before, where we're in this sort of new era of scaling of deep learning models, especially if you're counting by parameters. The last 5 or so years, models have been increasing by, on average 20x per year. And I don't think I need to tell you guys that actually the hardware struggles to keep up with that. And so we need to find things that we can use, tricks that we can use to make the hardware scale better. And of course, there is a large set of tricks that are out there. The one that we're going to focus on today is quantization. And sometimes this can't be entirely decoupled from things like and so what are the benefits? Your weights, if you can represent them using less bits, then that's less memory that you have to move around. It's also less likely that you'll be bottlenecked by, let's say, some low bandwidth external memory interface or something. For certain data types, this will also mean reductions in power for compute as well. And then I think these are all different sides of the same coin. I mean, lower power usually means you can make chips that have more dense compute. So, for example, on an MI300, you can get a 4x improvement from switching between, this is the compute performance between FP32 and FP8 or int8. And again, similar side of the same coin, you can reduce your amount of hardware area for the same amount of compute. So this is why we're doing this, and this is why this is helping to enable the sorts of scaling that we talked about in the previous slide, right? So what are we talking about with quantization? So I'm going to just give a quick visual example for integer quantization, and you could trivially sort of extend this to other types of quantization. Effectively, we have some continuous distribution of values, and we would like to be able to represent them using a small subset of values. So what we tend to do, in particular with integer quantization, is we scale those values to a range where our target integers can represent them. Then we do some sort of rounding, right? This is the process that actually performs the quantization. And then optionally, we might rescale to match the original distribution. And so you start with something like you have at the top, and you end with something like you have at the bottom. This is usually represented with an equation like this. Note, you can also shift your range, but I've just sort of omitted that here. But I would say every time you see this sort of equation, just sort of assume that in Brevitas, you can also shift the distribution and things like that, right? So it's a pretty benign looking equation, but for quantization researchers, this causes us enough headaches, let me put it that way. And just so you're familiar with the nomenclature in the neural network literature, the top three sort of lines of what I presented here, this is referred to as quantization, while the last step, the rescaling, is referred to as dequantization. And this whole process is sometimes sort of referred to as quantize, dequantize, or QDQ, or fake quantization. So going to give a very small side rant here. The neural network researchers have a habit of renaming things that already exist, and this is no exception. I would argue that what's written here as fake quantization, every other field in the world calls quantization, and there's maybe no need for this fake quantization term. And the top bit maybe should be considered conversion to integers. For a while, I was trying to get my colleagues to call this integerization. It didn't take off. It's a bit of a mouthful, to be honest. But I just thought I would mention that when you're talking to people outside of the field, expect some confusion about what quantization is. So here I mentioned fake quantization because this is the type of quantization that we do within Brevitas. So just to put this into a very small example, so for something like this very small dot product here, which forms the most of the compute that we're interested in optimizing in neural networks, we might have something like this at the top, which is represented by FP32 values or something like that. And we do some conversion to integers with some scale factor, both for the activations here represented by X and for the weights. And with just some rearrangement of our arithmetic, this means that we can do the dot product part. We could do this as in for compute with some post multiplication here. Let's say I've chosen maybe a bad value here, but an approximation to this scaling factor in FP32 or something like that. Now, this is when we deploy a quantized model, this is what we want to do. But I want to be clear that this is not something that we take advantage of in Brevitas today. In Brevitas, we're doing purely FP32 math. And basically, you will get a dot product between this vector and this vector. Okay? And then this leads to interesting questions like, okay, well, if I've introduced 1% error, is this good enough? Is this too much? And Brevitas is a tool that tries to help you get to that answer. Okay, so let's quickly talk about, here's our favorite equation again that looks again very benign. But let's talk about the sources of quantization error here. So really, it's the clipping and the rounding in this equation. And these you can think of as a trade-off between range and precision. So you can represent more values if S is larger. Yep. And but you will have maybe more round-off error within that range. And so here's two examples here. On the left, we're picking our S, our scaling factor, in order to be able to represent all the values in this range, but it incurs a large mean squared error over the entire weight distribution. Whereas on the right, we're better representing more of those values, let's say that are closer to 0, incurring a smaller mean squared error overall. But which is better here? And actually, it's not an easy answer. And I would say a good number of years of quantization research has been about how to calculate good values for S. And perhaps what to choose as your rounding function. Should rounding be, let's say, should it be tuned specifically for each value within X if it's a tensor? Things like this. And then popular post-training quantization methods go as far as maybe pre-modifying X or values in X before it goes into this quantization function. And so but it is quite interesting, at least to me, that this is what we're doing at the end of the day, is playing around with an equation like this, and it causes us so many headaches. I won't lie. Okay, so this sort of sets us up for Brevitas, which I would say is a tool that helps us answer maybe this last question in this slide is, how do we balance the trade-off of doing things like picking the right scale, picking the right rounding function, and so on and so forth, right? So first, I hope I don't bore you too much, but Brevitas has been around for a while. We've been doing this for a very long time. I'm going to give you a bit of a history of how Brevitas was conceived. For people out there who have looked at it or maybe want to look at it later, maybe this will preemptively answer you some of your questions about why certain things were done. So it was first open sourced in 2018. We targeted mostly very, very low precision compute, so binary and ternary weights and activations and very low precision integers. The goal at the time was to be the front end for FIN, which is a neural network accelerator generator for FPGAs, which also comes out of my wider team. And so we wanted to do things like answer the following questions, like which data type should we actually put into that hardware, or even maybe some fixed hardware that was being designed for the future. And or alternatively, given certain constraints on around bit width, how can we actually maximize the accuracy? And we used to make these little charts that you can see on the right, which is doing things like going through all different types of precision and trying to find Pareto optimal points between test error and some proxy for throughput, right? So trying to maximize throughput for some given test error, or for some given test error trying to, or for some throughput target trying to minimize test error. So I mentioned before, Brevitas has support for all your favorite data types, integers, arbitrary minifloats, group-wise data types, which can be further specialized to the MX data types. Our quantizers are very, very flexible. And this is sort of intentional. And I would say the reason why is because we're doing quantization research. We don't have the answers. We don't know what algorithms are the best ones, what algorithms are going to work with particular models. Our best strategy is to provide lots of options. And to do that, we design everything in a very modular way. And we optimize for composability. I'll talk a little bit about that in a second. We then provide preset quantizers with popular choices. And so I would say that these are the sort of outcomes of some of our research, is like, okay, in many cases, we see this combination of things are giving good accuracy results. So we should make it easy for somebody to instantiate one of those. Our quantizers are just made out of standard PyTorch operators with just a few custom autograd functions. And again, our goal is to be flexible, extendable, hackable, so that we can support new quantizers quickly, we can support new algorithms quickly, and I'll give an example of that later. Actually, yes, and so this, I'll go further into that example later, my apologies. This is an example of one of the research that one of our colleagues does, which is accumulator-aware quantization, and I'll delve into that a little bit later. So then, out of these quantizers, we provide then a library of quantized layers, various types of PTQ algorithms, quantization-aware training, and then we have pretty deep integration with PyTorch. So we have a quant tensor, which we use to propagate quantization information throughout the network. We lean heavily into FX for graph quantization. And because everything that we make is a PyTorch module, we get some stuff for free. So we get out-of-the-box support for distributed data parallel training, and we have interoperability with Hugging Face Accelerate. And a small flex at the bottom here, I think we're the only quantizer to support the entire AMD product range. So we're quite proud of that. So I mentioned modularity, and this is something that is important to us. And so I just want to highlight that a little bit here. We'll be going through various components in our software stack today. But the key point of the modularity and composability nature of our approach is that, you know, a quantized layer shouldn't really care so much about what quantizers are being used, and the quantizers shouldn't really care too much about which statistic you're trying to optimize for when you're defining your quantization scale factors. Quantized models are just PyTorch models that contain some number of quantized layers, And our PTQ algorithms, for example, shouldn't care about how you've constructed your quantized model. And so this is something that we're pretty proud of. And to give an example, so say our GPTQ implementation works with integers, works with mini floats, works with the MX data types. It works with, it's extended for activation, quantization, and convolutions, and those sorts of things. The exception to this is probably the export part, which does need to reach down and access the quantizers themselves to match the interface of the export target. Okay, so let's talk quickly about quantizers in Brevitas. I'm giving you a simplified example, but I think this highlights the approach that we take. So again, we do fake quantization. Our quantizers are trying to implement this equation that we mentioned before. And a simplified version of one of our quantizers looks something like this. So it itself is a PyTorch module, and it contains all these components, which are also PyTorch modules. And this allows us to do some interesting things. So for example, we talked about this scaling factor and the bit width before. These can be implemented by plugging in specific implementations, allowing you to add your own statistics here, or let's say learn a scale factor with backpropagation, apply arbitrary restrictions to scale factors like power of 2, things like that. And something that is not very common with quantizers is we have basically the same thing with bit widths as well. So you can actually do things like define gradients for your bit widths just by plugging in the right bit width implementation, right? Furthermore, this is where we plug in different rounding operations and different clamping operations. And these are examples of our custom autograd functions, because this is where we need to override the behavior of PyTorch's built-in autograd. Lastly, so all of our quantizers and their subcomponents are script modules. This is so that we can leverage PyTorch's JIT for performance. We are in the process of moving over to modules that can be better accelerated with Dynamo, which is sort of the latest version of PyTorch's JIT. JIT is being slowly rolled out and is in maintenance mode at the moment. So you saw that the quantizer, or that simplified quantizer, basically the implementations that provide everything are actually modules, right? And so I mentioned this is where we plug in loads of things. So for example, around the scaling factor, we can plug in different granularities. Do we want this to be a single scalar value for an entire tensor? Do we want it to be per some dimension of that tensor, or per some group of a subdimension? Do we want to restrict it? Again, floating point, power of 2. And how should we learn it? Is it some fixed value? Is it learnable with backpropagation? Are we plugging in some statistic there? The data formats, so most of my examples are sort of talking about integers, but yeah, we support, again, arbitrary floating point, logarithmic types, which is just a specific case of arbitrary floating point, and a bunch of PTQ techniques, which I will get into a bit later. So something I wanted to highlight, hopefully this doesn't scare people off, but I think it's an important look at some of Brevitas's internals. And if you want to leverage it for your own research, I think this is something that's worth knowing. These options that we have creates a very large space of components and subcomponents. And it can be pretty hard to get a handle on it. For example, so in order to instantiate a single quantizer, you might need to do what's written there on the right, which is a bit of a handful, right? Our approach to try to get a handle on it is to use dependency injection that basically tries to recursively go through each object and match attributes to the initialization parameters of each object to allow a sort of outside-in approach to instantiating quantizers. Now, this is something that we've written from scratch here. This is something that in general a user is not expected to do. But these are all the things that you could customize for a basic affine integer quantizer, right? Cool. So, okay, we talked about quantizers and how to instantiate them. Now we need to put them into layers to get some sort of quantized module. Okay, so there's 3 different approaches that we take. So this first one is the so-called manual approach. This is where you do something like what I've shown here, which is to take a floating point network written in PyTorch, rewrite it also in PyTorch, but use our library of quantized layers. And here, applying a single extra argument, which is just the definition of one of our weight quantizers. Here's one that's prepared earlier. So this is an int8 weight quantizer with a per tensor scale that is a floating point value, right? And so these networks, these would be state dict compatible, right? So you should be able to load the weights from one into the other. And many users actually leverage this flow. And I bring this up because I think this is a bit uncommon for a quantizer to target this manual sort of flow. But this is where you get the finest control over the type of quantization that you want to actually do. And so many users actually use it. An alternative approach is to use a programmatic layer-wise approach, right? And so this is where you do something like what I'm showing here, which is to use this so-called layer-wise quantize function and to provide a map. And the map is telling the layer-wise quantize function how to convert layers of interest into the type of quantized layer that we want. And there's all sorts of exclusion lists that you can add to this and so on and so forth. But effectively, if you write the code that I'm showing here, you will get something that is functionally equivalent to the changes that you made to the network in the previous slide. Now, for most users, they're probably not going to implement their own map. Basically, this is something that we do as the Brevitas team to come up with a set of preset maps to support particular pieces of hardware of interest. So realistically, you're not defining your own map. You're maybe instead specifying one that's associated with a specific target. So one of the issues of this sort of approach is that we only look at the network from a module by module point of view. We never see the full compute graph of the network. And we also can't see PyTorch functional operations. So if somebody just writes a map mol with a weight in the middle of a layer, we can't see that that's functionally equivalent to a linear layer.
experience some technical difficulties. So let's wait for Nick for a second.
Hey guys, can you hear me?
Yes, we can hear.
Sorry about that. That was complete laptop switch off, blue screen of death multiple times. So let me just load up my slides.
Yeah, okay. No worries.
That's a first for me, and I won't lie. That's with the day I'm having, that's fitting. So let's get back to it. Just give me 2 minutes to bring up the slides again.
Sure.
Okay. At least there have been no doorbells and fireworks, so that's been a good start. Okay. My computer's so slow. Okay, so let me share again. Okay, I believe I was on this slide and almost at the end. Did you catch most of this slide?
Not really, I think. I mean, yeah.
Okay, all right. So I'll start again for this slide from this slide.
Yeah.
Yeah. So basically, we had this previous example. Oh, sorry. I think yeah. So we had this previous example where you manually rewrite your network in a way that's state compatible, but now has quantization operators applied to the weights. And then there is alternatively a programmatic approach. So this is, sorry, just 1 second. So programmatic approach. So this produces a network that is functionally equivalent to the quantized network in the previous example. It's still state-dict compatible. Actually, in this case, the state-dict and the weights effectively will automatically be carried over to the quantized network. And it's this map that is controlling how this map dict that is controlling how each PyTorch layer should be converted into its quantized equivalent. And there's various things like exclusion lists that you can apply to have very tight control over having specific layers of having certain layers of, let's say you want a different quantization for 2 types of linear layers. You could handle that through exclusion lists. And so what's good about this is that this allows you to do something for, say, a very complex network that you don't want to rewrite. Let's say one from somewhere like Hugging Face. You could programmatically say, okay, I want all of the linear layers to behave like this, or I want all of the linear layers that match this name association. So this would be their sort of fully qualified name from the PyTorch sense to be converted in a specific way. Now, in general, we're not really expecting users or your standard users to write these map functions themselves. It's something that we usually provide, and we have specific examples for specific targets. So one problem with this sort of approach is that we never see the whole computational graph of the neural network. We only look on a layer by layer basis and do replacements. And this means that we don't see any custom code that somebody has written that is not a PyTorch layer. So if somebody decides to instantiate a weight and do a map mul between that and some activation tensor, we won't see that this is functionally equivalent to a linear layer. And so if you're doing this, you may need to still make modifications to the network in order to quantize all the important operations in the network. And we do have some infrastructure to help with this. Most of that infrastructure is based on effects. So we leverage effects in multiple ways. And I think has to be able to understand the very brief example here. So this is a subgraph of a ResNet 50. And if we wanted to implement a ResNet 50 in hardware using full integers, then we would need the scale factors associated with these quant nodes. We'd need them to match. And then this add here, this add can be implemented as an integer add instead of at hardware time needing to be dequantized and implemented as a floating point value. So this is circling back to what I talked about before, which is how you rearrange these operations to do this low precision compute. This is something that we leave to the back end. So I'm seeing that I should sort of speed up because I lost maybe 10 minutes there while I was sorting out computer issues. So I'm going to go fast for the next little bit. Apologies in advance for that. The last thing that's good about the way we leverage effects, so this can be useful in doing things like data-free equalization, smooth quant, batch norm merging, things like that. So, and we usually refer to these as quantization adjacent functions. So, for example, like can you apply some channel-wise scale to your weights to make it so that it's easier to quantize with a per tensor quantizer? And if you do that, then you're going to have basically an output that's equivalent to your original output, but it's going to be scaled in some way. And if we have full access to the compute graph, we can go and search through the graph and see if we can merge that per channel scale with some other linear operator that's in our network. So achieving good accuracy. So now we've just talked about how to instantiate quantizers, how to attain a quantized model by inserting them into places in the network. Achieving good accuracy is then, this is the starting point for now trying to achieve good accuracy. So one thing that you could do is you could do quantization-aware training. As I mentioned before, Brevitas modules are just PyTorch modules, so you can just train it in exactly the same way as you did before. And often that's a pretty good starting point, is to take the same training loop that you may have taken to train your neural network module of interest and use that exactly the same with the exact same hyperparameters, but with the quantized version of the model. There's also extra things that can be taken into account to, say, optimize the network further. Like, for example, I mentioned learning bit widths earlier. These can be incorporated into custom loss functions to allow some trade-off between minimizing your standard sort of task loss against some proxy for inference cost of your network. We also have several PTQ algorithms that can be applied on their own or in combination. Some of these are in the category of these sort of quantization adjacent algorithms like activation equalization and weight equalization, whereas others are very much intertwined with the quantization process itself, like GPTQ and GPFQ and so on and so forth. And we've tried to have a unified interface for all of these PTQ algorithms. And so basically there's lots of options for you to try to get good accuracy out of your network if you're using PTQ. I'm going to go quick over these results. The point here is that PTQ is pretty great. It can get you a long way, but usually it has some limit. It has some cliff where, at least for some models, you start to really, really underperform. And so this was taken from one of the publications that came out of my colleagues a while ago, looking at combinations of different PTQ algorithms and trying to get the best for each of these networks. QAT, in my opinion, is still the best way to achieve maximum accuracy if it's feasible. And so taking the ResNet 18, for example, before, we can actually achieve better accuracy than the baseline FP32 module. Now, that may seem a bit confusing. How could a quantized model be better than a FP32 model? There's a lot of theories in the literature about this. I think the reason most people tend to give is that quantization here is behaving as some kind of regularizer that is helping generalization. Similarly, we've expanded to LLMs. This is just a small example. One thing that we have tended to see is that for smaller LLMs, it's much more difficult to quantize the weights, while for larger LLMs, it's more difficult to quantize the activations. And so this is just some examples that we have using our GPTQ that's been extended for activation quantization. So I mentioned that you could learn precision learn bit widths with Brevitas. This can be done on something like a per layer basis. And so this is just a bit of a motivating example. If this is our floating point mobile net, at constant precision, we can achieve the following validation errors for the corresponding compute cost. Let's think of this as a proxy for how long it takes to do a single inference. So on your right, it's taking a very, very long time to do a single inference. And on your left, it's taking a very, very short amount of time. So if you learn the precision with Brevitas, you can achieve something that has an overall average of a very low bit width, but achieving something that is still doing, let's say, higher accuracy than 4-bit constant precision, right? And this is because some layers will be at higher than 4 bits, but a lot of layers will be much, much lower, right? So this is what I mean here about bit width is just another parameter, and we can learn it with backprop. Now, I wanted to go a little bit into this, but I'm just seeing that maybe we don't really have time. What I wanted to highlight with this part is that you can also leverage Brevitas to do interesting quantization research. And in this case, we're interested in quantizing accumulators. In certain FPGA implementations, this means less hardware. In CPU implementations, if you can get your accumulator down from 32 bits to 16 bits, something like that, you can sometimes double your performance depending on what intrinsics are available, what instructions are available. And so the idea is we sort of flip this paradigm on its head. And instead of thinking about our data types and calculating what's the maximum accumulator, we try to optimize our weight values to ensure that our accumulator will never overflow within some specified bit width. And this involves incurring some sparsity, which I sort of hinted at earlier within your weight tensor, but doing it in a way that is overall produces something which is Pareto optimal in the examples that we have. And just some quick results against, doing some sort of brute force heuristic kind of bit width manipulation against this accumulator-aware quantization. And basically what needed to happen from the Brevitas side is a custom quantizer needed to be implemented that was aware of accumulator bit widths and did that so that this could be optimized for. So I wanted to leave time for questions. So that's my very, very rushed version of going through these slides. What I would tell you is go and read these papers that have extended this if you're interested. So key takeaways, neural networks, I think as we all know, mostly dot products, and quantization allows us to reduce the cost of these dot products and their underlying cooperation, max. This tends to come with a reduction in model accuracy, and this is the goal of Brevitas, to provide you with as many tools as possible to limit the amount of reduction in model accuracy, or to maximize your model accuracy within given certain quantization constraints, however you want to think about this. We provide you with loads of tools. You can use them in combination. Our goal is that everything should be composable. Every PTQ algorithm should work with every data type, and you should be able to do quantization-aware training with any sort of data type if you want to, right? Lastly, it's open source, modular, extensible, and maybe you've heard enough today that you might consider using it for your next project. We're looking to collaborate with people such as yourselves. Hopefully this is not just a one-way thing. I hope that you get a benefit out of it, and I hope that this means that when you guys are coming up with new algorithms, that you're considering making a PR to Brevitas so that it continues to track a lot of the latest research. And that's it for me. Sorry about rushing a few pieces there. Yeah. Any questions?
Thank you for your presentation, Nicholas. I just wanted to take right now a short period of time to let you know about the next speaker that we're going to have in 2 weeks. At 6 p.m., we're going to have Martin Schulz from University of Cologne talking about deep learning and how it can beat numerical weather predictions. Also talking about, the future directions in numerical weather prediction. And now Any questions? If you have any questions, please put them either in the chat and then I will read them out, or raise your hand and I will unmute you. Okay. Let me start myself maybe then. So I really like this view of looking at quantization as fiddling with this one equation that you mentioned at the beginning. My question would be, you know, in your feelings, where is the limit to this fiddling? So how far can we go with this? And what are you also going to aim at next in your sort of like pipeline of development of Brevitas?
Yeah. Okay. Those are great questions. The limit of this. Okay, so my feeling is that this is always going to be. I just used an absolute. I don't like using absolutes. It's most likely going to be network dependent. So my suspicion is, as people are applying neural networks in many, many areas, you're going to have things like your family of mobile nets that are notoriously difficult to quantize, and you're going to have things like certain LLMs where they're sort of very easy to quantize. So I suspect that there seems like there's slowly a race to the bottom in terms of bit widths. There's even recently people doing these papers looking at they describe them as map-mole-free LLMs and achieving good performance. So I think we're going to have to be ready for everything. One thing that I always think about is a paper that I read many years ago. I think when Johannes, who may still be on the call, was also an intern at Xilinx at the time, about binarization of dot products. And this work showed that theoretically, the larger your dot product, the more the angle between your vectors was preserved during the binarization process. And so my intuition for that is that as dot product sizes continue to increase, we'll continue to be able to at least reduce weight precision. This creates some extra challenges and activations, but I think weights make a lot of sense. What's the next with Brevitas? We're constantly doing new things. So one of those papers I linked in the accumulator-aware stuff was extensions to GPTQ to make them aware of the special accumulator quantizers and make them work better for that. So I think we still want to make contributions in research, even if they're small ones. At the same time, I think also we want to consolidate a lot of the good work that we've done in Brevitas and try to help new users use it a bit easier. So improve documentation, improve testing, write more tutorials, make more examples, those sorts of things.
Thank you.
Okay, thank you, Hello. Thank you for your very interesting presentation. Unfortunately, I was a bit late, so I'm sorry if this covers something that you mentioned in the beginning. You also showed some results for transformer networks, and I was wondering how the nonlinear operators in these networks are supposed to be handled, especially in the backend, and if they are supposed to be, or if you assume that they will be handled in a dequantized format. And
Yes.
the main point, or the reason I'm so interested in this, is because what I've seen is that especially if you run this on hardware accelerators, that you are able to compress a lot of like your arithmetic operation in a very short time with your accelerator. So you're kind of able to accelerate it a lot, but then you kind of become blocking for these nonlinear operations. And even though they're arithmetically not very intense and you spend a lot of energy on this.
Yeah, yeah. And at the end there, you're perfectly sort of describing it's Amdahl's law, isn't it? You know, like we spend so much time on the dot products that the bits that used to take 1% of the time maybe now take half the time because we've improved the performance of our dot products by maybe a factor of 100 or something. Okay, so how to handle these nonlinear operators. So a good example in Fin is if the operators are monotonically increasing. This can be handled by thresholding. This only scales to this will scale exponentially in bit width. So it probably doesn't really make sense beyond let's say 6 bits, something like that. Beyond that, it starts to cost a lot. I think for a lot of these operations, my intuition is that these maybe need to be handled with like subdivisions of lookups with linear or polynomial interpolation. Now, this doesn't really, this might not make sense for every hardware architecture that there is out there, but that's my intuition for how to handle these. So you've got two options there. I don't think this is a solved problem, even with both of my options there. I'm sure there are some activations where that doesn't make sense. Okay,
thank you. So you're saying, for example, for softmax, that like the iBird approximation is something that makes sense. So how much is the effort, or do you already support this in Brevitas, especially also the open source version on GitHub? Or
got it. Okay. Yes, softmax is a good one. So softmax it has some properties that we can take advantage of. So for example, softmax is shift invariant. So anything that we do on the quantization side that's a shift shouldn't affect the output. How we've done this in the past is let me think about this. So we have done this, but you're testing my memory now. So is there, I can't remember if there's a transformation, because as you say, dequantized input for softmax, when you scale the input, this is effectively changing the base of your exponent. Is that how this works out? Something like this. There is a trick that you can do as well to
exactly, you can change the base and then absorb this change into the requantization of the input.
Yeah. So thanks for testing me on that one. So that's what we have done in the past, and then there's all these little tricks that I'm sure you've seen in Flash Attention for trying to implement softmax in a way that is that rearranges some of the compute to do things in a fused way while also trying to minimize issues that you would have with range. So softmax is a bit of a special case. There's plenty that can be done there. Usually doing quantize dequantize operators before and after the softmax is is how we've done this, and basically rearrange things and changing the exponent, like you say. There's also options to kind of unpack the, let's say in attention, unpack the map moles and apply the fusion, but then the quantization operators need to be placed in really specific components. We haven't done this in Brevitas. What this would require is let's say PyTorch level code that implements this, knows the tile size that you're using to fuse these operators, and quantize those components in the way that makes sense. Unfortunately, not a very good answer. I would say this is one of those components where if we wanted to implement quantized flash attention, that there would be a little bit of work on the layer level that would have to happen. We try to avoid it because the tile size is often quite hardware specific. And so you've got this feedback that you need to apply into your quantization procedure that makes everything a lot more complicated, but this would be possible.
Okay, thank you. I have more questions, but I also don't want to steal questions from the others. So
good. Thanks for the questions.
Thank you for the good answers.
I think I don't see any other questions. So if you want to go forward with your questions, Philip.
Okay, I have one more question. It's a bit about the backend. Sorry, I think this part I missed. I was a bit late. So you mentioned it afterwards again that you kind of shift the transformation between a fake quantized graph and I call it true quantized graph to the backend.
Yeah.
Where you effectively you kind of you have usually have the dequantize and the quantize, right? And you the other way around, and you propagate the dequantize through the operators.
Yeah.
And then you can merge the dequantization and the quantization into a requantization, right? And this part is, I mean, it's straightforward for linear operators because you kind of can ignore the scaling factors. But as soon as you have other things, it gets tricky. And so far, the way I understand is that the main backend is Fin. And I have to be honest, I'm not very familiar with this. So is this the framework, or is this the backend I should look at to see how you guys do this? Or do you also have other backends that you are targeting?
Yeah, so let me answer your question at a global, at a zoomed out sense first. So our opinion is, and I'm open to criticism, is that this sort of rearrangement of operations is like a something that could be well handled by a compiler in a way that is probably a lot more robust than we can do it at the sort of PyTorch level in Brevitas. It wouldn't be impossible, of course, but this is something that we view as something that a compiler should be able to do quite well. And so that's our rationale for pushing these things down. And usually we're quantizing networks in a way where we have some sort of understanding of what the compiler should be doing. So then on the specific case, so Brevitas was indeed made for Fin. I would say we support the entire AMD product range today. Fin just also comes from the same group, so we, of course, have a very good collaboration. But I think you could look into Fin, and the way these operations are referred to in Fin is streamlining. And so if you're interested, and you want a few pointers, I don't think I shared my email in the slides, but you should see it maybe in the invite, or please, Marcin, please send this around to the invite list. I'm happy for people to reach out to me for pointers. I can send you a paper that we've written about streamlining, as well as point you to the guys in Fin that can show you the specific transformations in Fin where this occurs.
Okay, thank you very much. Yeah, I'm familiar with the that this is called streamlining, but I just did not yet have the time to dig deeper.
Yeah, fair enough.
Thank you very much.
Yeah, no worries. Yeah.
Sorry, Philip. I just put the email in the chat right now, so if anyone wants to use it, feel free to pick it up from there.
Perfect.
Thanks for that.
Good. Thank you, Dan. I don't think we have any other questions. Thank you for the great presentation and the answers to the questions.
Thanks for having me and standing by while we persevered through my interesting computer problems. Thanks. I appreciate everybody and their time.
Thanks. Bye.